Uh, in the previous session, we were discussing about the optical filters that are used in WDM techniques. In optical filters, the fiber Bragg rating and gating techniques, etc. We were discussed. Uh, Now we are going to discuss about the tunable optical filter. The tunable optical filters are key important for dense WDM optical networks. So several different technologies that can be used to make a tunable filter. The two key ones are MEMS based and Bragg rating based device. I think all of you are familiar with that term MEMS. And the two key ones are one is MEM based techniques and another one is Bragg rating based devices. MEMS actuated filters have the advantages characteristics of a wide tuning range and the design flexibility. Fiber Bragg rating are wavelength selective reflective filters with a steep spectral profiles and flat tops. They are the important things regarding the MEMS based filters and the Fiber Bragg based filters. For a 100 gigahertz filter, that is a reflection bandwidth of less than zero point 0.8 nanometer at a 25 dB below the peak. Standard uniformly spaced fiber grating having large side lobes, which lie only about 9 dB below the central peak. I think all of you familiar with the term side lobes in the antenna theory. I think you are familiar with that. However, these side lobes can be reduced. I think these side lobes are presence of side lobe is undesirable because we have to minimize the side lobe powers and side lobe presence. So these side lobes can be reduced to be at least 30 dB below the peak by using special apodization mask. This apodization mask is used to reduce the side lobe level. That is to precisely control the ultraviolet beam shape in the Bragg grating fabrication process. Apodization is a mathematical technique that is used to reduce ringing in an interference pattern, thus giving a large central waveform peak with a low side lobes. So one way of creating a fiber grating is by using ultraviolet light to set up a periodic interference pattern in a section of the core of a germanium adaptive silica fiber. This pattern induces a permanent periodic variation in the refractive index along the core. Tunable optical filters based on fiber Bragg grating involves a stretching and a relaxation process of the fiber grating. Since glass is slightly stretchable medium, I think all of you know the property of a material, the glass is used for the optical fiber. This glass is a slightly stretchable medium. So as an optical fiber is stretched with a grating inside on it. So the spacing of the index perturbation and the refractive index will change. This process induces change in the Bragg wavelength, thereby changing the center wavelength of the filter. Such optical filters can be made for the S, C, and L bands and for operations in the 1310 nanometer region. So these are this can be used in the different bands as S band, C band, L bands, etc. The tunable grating technology, before it is structured, the center wavelength lambda c of the fiber Bragg grating filter is given by lambda c equal to 2n effective lambda, where n effective is the effective indexes of the fiber containing grating, and the lambda is the period of the index variations of the grating. So when the fiber grating is elongated by a distance, so uh, when the fiber grating is elongated or expanded by a distance, that is there should be a delta lambda. This corresponds to a change in the center wavelength, that is central wavelength lambda c equal to 2 times n effective lambda. Here if we are changing, if we can change the we can produce a change in lambda, that is delta lambda, that is due to the elongation of the fiber. So that this elongation, so this expansion, that results a change in delta lambda, that is we can make a corresponding change in the center wavelength, that is delta lambda c equal to 2n effective delta lambda. So this expansion or this elongation or this extension or this change in lambda, we can produce either three methods. The stretching can be done by either three methods. One is thermomechanical, piezoelectric, or stepper motor means. All these are the three different techniques we can see in the figure. So this stretching, the fiber stretching can be obtained by thermomechanical method. So you can see in the first one is the thermomechanical method, and another one is a piezoelectric method, another is stepper motor method. By using any of these three methods, we can stretching this fiber material, and we can make the change due to this stretching, that is the change in lambda. This change in lambda is resulting the change in the center wavelength, that is delta lambda c. That is actually is the tuning. I think all of you know the tunable filters, normal case LC tunable filters. I think all of you know about that. Is while we are changing the either changing of the inductance or either changing the values of the capacitance, we can tune that filter into a particular frequency, that is LC tuned filters. Then that filter filtered out to the tuned to that particular frequency, it can pass only that particular frequency. As same way, the optical filter, we can we have some tuning, that is here, that's tuned optical filter. This tuning, that's change, how we can change the center frequency, center wavelength. The center wavelength, the center wavelength can be tuned by using these three methods. The first one, the thermomechanical method, might used by a bimetal differential expansion element, which changes shape as temperature varies. That is, as its temperature varies, the shape varies. So in the figure, high expansion bar changes its length more with the temperature than the low expansion frame, thereby leading to a temperature-induced length variation in the fiber gratings. You can see in this figure a high expansion bar and heat from the heat from that is heat is applied, or that heat is applied to the high expansion bar. From the using that heat, high expansion bar may extend or that may change its shape, or its length may change. That is, as the temperature increases, they may occur some expansion. That is high expansion of bar changes its length is more in the more with the temperature. That is thereby leading the temperature induced length variation in the fiber grating. So this change in length, that due to the temperature variation. So but due to this change in length, we can change the center frequency. So that we can change, whether we can tune to a particular center frequency. So this method is inexpensive, but it is slow, takes time to stabilize, and has a limited tuning range. Another one is called the piezoelectric technique. So the piezoelectric techniques is nothing but that piezoelectric techniques uses a material that changes its length when a voltage is applied. I think all of you familiar with the piezoelectric techniques. Where piezoelectric techniques is nothing but that when we are applying when we are applying an electrical field on the opposite faces of a piezoelectric crystal, so that may result a mechanical vibration or elongation on the opposite face. So the reverse also possible. That is the piezoelectric effect. So this method provides a precise wavelength resolution, but is more expensive than complex implement. It has a limited tuning range. That is, when the this material can change its length when a voltage is applied as per the piezoelectric effect. So as per the piezoelectric effect, while we are applying an electric field or voltage, then the length or that they may change its length. These due to this change in fiber brag length or fiber length, we can produce a delta lambda. So this delta lambda is corresponding to the change in delta lambda c, that is change in the center frequency. That's why we can tune, or we may tune or particular wavelength by using this method. So another thing is the stepper motor method changes the length of the fiber grating. So by pulling or relaxing one end of the structure, you can see the figure, that is stepper motor method. Okay. Uh, it has a moderate cost, it is reliable, and has a reasonable tuning speed. One tunable filter variation version as a tunable variation on the classical structure that has been used widely for interferometer applications. So the device consists of two sets of epitaxial layers that form a single family throat cavity. Its operation is based on allowing one of the two mirrors to be moved precisely by an actuator. This enables the variations of the distance between two cavity mirrors, so thereby resulting in the selection of different wavelengths to be filtered. The distance variation can be achieved by any of the three methods described, if that is thermomechanical method, or either by thermomechanical or the piezoelectric method, or by stepper motor method. So either of these three methods described above for the tuning rating. So so here in the table that is showing the performance parameters of the tunable optical filters, that is the parameter and specification. The tuning range is around 100 nanometer typically, and the free spectral range, that is FSR, that's 150 nanometer typically, and the channel selectivity 150 and 25 gigahertz, bandwidth less than 0.2 nanometer. Insertion loss, I think you know the insertion loss, and we have discussed in the previous session. Less than 3 dB across the tuning range, and the polarization dependent loss at PDL, that is less than 0.2 dB across the tuning range. The tuning speed and 10 nanometer per microsecond is in both C and L bands. Tuning voltage is 40 volt. So application, so gain tilt monitoring in optical fiber amplifiers. They are the applications of these um, these tunable filters. The gain tilt monitoring optical fiber amplifiers, and optical performance monitoring in the central offices, and channel selection on the receive side of the WDM links, and suppression of amplified spontaneous emission. Yes, the noise in optical fibers. So these are the applications. Okay.